Introduction. In this lab, we explored Kirchhoff's rules to understand how current and voltage behave in a complex electrical circuit. These rules come from the conservation of energy and charge, which means that energy and electric current cannot be created or destroyed, they just move through different parts of the circuit. Kirchhoff's current law states that the total current entering a junction equals the total current leaving it, while Kirchhoff's voltage law says that the total voltage rises and drops around any closed loop must add up to zero. Together, these two rules let us analyze circuits that are too complicated to solve using Ohm's law alone. For this experiment, we used a multimeter and the Pasco capstone setup to measure current and voltage across several resistors. Each resistor was labeled and measured individually, and then the circuit was built based on the schematic provided. We measured the current through different resistors and the voltage across them, recording the results digitally for better accuracy. These measurements were then compared to the theoretical values predicted by Kirchhoff's rules. The purpose of this lab was to confirm whether the measured data followed the relationships expected from the junction and loop rules. By comparing the sums of the currents and voltages, we could determine if charge and energy were conserved within the system. Any differences between theory and experiment helped identify possible errors, such as extra resistance in wires, small connection issues, or sensor inaccuracies overall. This lab helped us see how Kirchhoff's rules apply in real circuits and deepened our understanding of how electric charge and energy are balanced in every part of a circuit.
For this experiment, we used 4 resistors, each labeled from 1 to 4 with small pieces of tape, so we could easily identify them in the circuit. We used a digital multimeter to measure the resistance of each resistor before connecting them. To collect data, we used a current sensor in series and a voltage sensor across each resistor to record the current and voltage values. All the components were connected using wires and clips following the circuit schematic. The power for the circuit came from a DC power supply set to 7 volts with a voltage limit of 10 volts and a current limit of 1.1 amps. Finally, we used Capstone software to display the current and voltage readings in real time using the digits display. These materials allowed me to build the circuit and verify Kirchhoff's rules accurately. Today, we're performing an experiment to verify Kirchhoff's rules using a circuit with 4 resistors. We'll measure the current and voltage in different parts of the circuit to test the junction and loop rules. First, we labeled each resistor from 1 to 4 using tape, so we can easily identify them throughout the experiment. After measuring the resistors, we built the circuit following the schematic provided. For each trial, we placed the current sensor in series with the resistor being tested and the voltage sensor across it. In Capstone, we set up 2 digit displays, one for current and one for voltage, and changed the current units to milliamperes. In the signal generator, we selected direct current, set the voltage to 7 volts, voltage limit to 10 volts, and current limit to 1.1 amps. We then connected the voltage and current sensors for resistor 1, clicked record, waited 2 seconds, and clicked stop. We repeated this process for each resistor and took screenshots of our readings. Resistor 1, you're connecting the first resistor circuit so the sensor can measure between R1 and R2. R1 is connected to the negative side of the sensor. R2 is connected to the positive side. R3 and R4 link everything together to complete the circuit. Resistor 2, You're connecting this one with R3 and R2 going to the sensor. R3 goes to the negative side. R2 goes to the positive side. The other resistors, R1 and R4, connect between them. Resistor 3. This one is the same as resistor 2. R3 and R2 are still connected to the sensor's negative and positive sides. R1 and R4 just help link the parts together. Resistor 4. This one is flipped around. R4 connects to the positive side of the sensor. R1, R2, and R3 connect in a chain that leads back toward the negative side. Finally, we analyzed our data using Kirchhoff's rules. We calculated the percent differences and compared our measured values to the theoretical predictions.
Said Gregorio Canton, and today I will go over the data analysis for lab number 5. The setup for this lab, as previously discussed, was that we would have to measure 3 different resistances, measure their voltage and their current in a circuit that was set up exactly like this. We had to measure whatever voltage and current they gave out and then compare that using Kirchhoff's law to see if the percent error was adequate. These were the experimental values for this experiment. For resistor number 1, we had 2.62 volts and 40.497 milliamps. We went down each of these resistors. As you can see, some of them have a negative, but this is just due to the polarity. Taking the absolute value gives us the adequate voltage to compare each one of these, and also the correct ampage. Here is a quick diagram of where we would ideally put the sensors to measure the current or voltage passing through each one of these resistors. You can see resistor 1 would be here, resistor 2, resistor 3, and resistor 4. The setup itself, due to our sensor, was different, but in theory, this is how it would go. This is a current and voltage table. Our source voltage was 7 volts, and the source ampage current was 1.1 amps. Here is all the values listed as seen before with the experimental data. Now, for these calculations, we have to understand that Kirchhoff's law, or rather, all these calculations stem from conservation of energy. We can equate some current or voltage as the layout of our circuit mimics the addition of the current passing through certain resistors or the voltage passing through certain resistors. They should be equal. And as such, we observe that this is true with extremely low percent errors, going down to 1.6% at its max and 0.38% error at its minimum. Really good numbers. Finally, this is a percent error table. Here we listed the previous equations just organized, comparing the current passing through resistor 4 and the summation of the current passing through resistor 1 and 3, which should be equal to the previous one, which turned out to be pretty close. Same with source voltage and the voltage in resistor 1 and 4, and the voltage in resistor 1 with the voltage in resistor 2 and 3. This was everything for the data analysis. Thank you.
In this lab number 6, we applied Kirchhoff's rule, 2 fundamental laws for electrical circuits to analyze our own circuits, and verified the conservation of energy and charge within electrical loops and junctions. Using a multimeter and a current sensor, we measured the voltage across and current through multiple resistors connected in the circuit powered by a 7-volt DC source. Kirchhoff's junction rule stated that the total current entering a junction must equal the total current leaving, while the loop rule states that the sum of the voltages rises and drops around a closed path must equal 0. Our experimental data supported both Kirchhoff's rules within a reasonable percentage difference. The measured currents in the branches in the circuit showed that current through resistor 1 plus current through resistor 3 should almost equal to the current through resistor 4, confirming current conservation at junction. Likewise, the measured voltage around the loops were consistent with the theoretical exceptions based on the loop rule. Small differences were observed and reflected by percent differences of about 1.2% error in the current relationships, a 1.6% error in the voltage source, and a 0.38% error in the voltage across resistor 2 and resistor 3 being equivalent to voltage across resistor 1. These discrepancies likely resulted from internal resistance in the multimeter, loose wire connections, or slight variations in resistor tolerance. To minimize these differences, using a tighter tolerances, ensuring secure wiring, and recalibrating the multimeter before the data collection would help improve accuracy. Overall, in this lab, successfully demonstrated the validity of Kirchhoff's rule and current voltage rules, and their importances in the understanding of how current and voltage behave in electrical circuits. It reinforced the concept of conservation of energy and the charge, and showed how experimental limitations can influence circuit measurements.
Credits: Introduction, Geomaterials, Pedro Procedures, Pedro Data Analysis, Seath Conclusion, Aaron.